Okay, before we get started, a couple of reminders. One is that we have the homework that's due today, so please send that to me if you have not done so already. There will be another homework in a few days, not just yet, coming up in a few days. And then we have the midterm that we decided would be next Thursday, right? And here, I have to apologize to you guys. I'm so embarrassed. On the day when we were talking about the midterm, after the class was over, and I was downloading the video to post on Google, there was a text chat to download also. And one student had typed some objection to that date and time in the text chat, which I just hadn't seen. It is so embarrassing for me. I normally just don't see the text chat that you guys might post during a class. I'm not quite clear why I don't see it. I think it might be that maybe while I'm sharing the iPad screen, the text chat shows up in a funny place that I don't look at. So, well, I could say a specific thing or a general thing. My specific thing is, does anyone still have a problem with the midterm time? And if so, please speak up on text chat or on voice or on video, or send up a smoke signal or something. No, I'm not hearing any problems. Okay, well, if I don't hear any problems and I don't see any problems on the text chat, then I guess there are no problems, I guess. Yeah, in general, I guess maybe I'm not so good at multitasking. I don't use text messages that much in real life either. And so that just shows how old I am. And so I will try to adapt, and I'll try to pay attention to wherever the text chat shows up. So I'll do my best for that. And can you guys try to meet me halfway on that? And so that means that if you send something in the text chat and I look totally oblivious, like I don't even know that you're typing something, I probably am totally oblivious. And so, but please speak up if you have a microphone and you just say, excuse me. And I say, okay, what would you like to say? And then you say it, right? Or if you notice that some other student has posted something in the text chat and maybe that student doesn't have a microphone, you can say, excuse me, there's something in the chat that you want to know about. Okay, so please do that for me. So help me out. Anybody there who has a microphone and has good multitasking skills to pay attention to that sort of thing. All right, we'll muddle through here somehow. Good. So in that case, let's talk about eigenvalues and eigenvectors. So this is a math subject, which is not particular to quantum mechanics, but it shows up a lot in quantum mechanics. And so I want to go back and refresh your memory about the basic math idea, and then talk about how we apply this to operators in quantum mechanics. Okay, so I'm going to do this first with matrices and then with operators. Okay, so with matrices, and let's think, to be specific, about 2 by 2 matrices. Okay, so let's start by talking about some examples. So let's first think of the example of the matrix A is 1, 0, 0, 2. Okay, so this matrix is real and it is diagonal. Okay, so the word diagonal here means that it only has non-zero elements on the main diagonal, which is like this, the diagonal that goes from the upper left to the lower right. Okay, so everything that's not on the diagonal is zero. The elements on the diagonal might be zero or non-zero. Okay. So in this situation, if we want to know the eigenvalues, that's really easy, okay, for a diagonal matrix. Because with a diagonal matrix, the eigenvalues are the numbers on the diagonal. Here, I'll write that down. The eigenvalues are the numbers on the main diagonal. So in this case, 1 and 2. And the eigen vectors are just the vectors in the special directions, the coordinate directions. So 1, 0, and 0, 1. Okay, so let's check that. Okay, so the eigenvalue equation is that A, matrix multiplication with a vector, is the eigenvalue times that vector. Okay, so and I'll label this, right? This is the matrix. This is the eigenvector that goes here. And here is the eigenvalue. Okay, so if we want to check this, we could say, what is 1, 0, 0, 2 matrix multiplication of that with the vector 1, 0? Okay, so you remember how to do matrix multiplication, right? That is, on the first thing in the matrix product, you go across the rows, and then the second thing, you go down the columns, right? And then you multiply element by element. Okay, so on the top, oops, wrong pen. On the top, we have 1 times 1 plus 0 times 0. Okay, so that's 1. And on the bottom, we have 0 times 1 plus 2 times 0. So that's 0. And we say, oh, okay, so that is equal to the vector that we started with. Or in other words, it's 1 times the vector that we started with. Okay, so that means that the eigenvalue is 1 and the eigenvector is 1, 0. Okay, or let's check the other one. So for the other one, we have the matrix A, that's, oops, excuse me, 1, 0, 0, 2 times 0, 1. And this product well, on the top, we have 1 times 0 plus 0 times 1. So that is 0. And on the bottom, we have 0 times 0 plus 2 times 1. That is 2. So here is our vector 0, 2. And this is equal to 2 times the vector that we started with, which was 0, 1. Okay, so the eigenvalue is equal to 2, and the eigenvector is equal to 0, 1. Okay, now let me just point out something. Well, I can point out a couple things as we're going along. Okay, I'll say, notice that there are 2 eigenvalues. Okay, in general, the number of eigenvalues is equal to the dimension of space. Okay, the dimension of the vector space. So here we have vectors that have 2 components, right? Row number 1, row number 2. Okay, and the matrix is 2 by 2. So that's what gives us the 2 eigenvalues. If we had a 3 by 3, then there'd be 3 eigenvalues. Okay. Another thing to notice is that the eigenvalues are real. Okay. Another thing to notice is that we can multiply, well, there's 2 eigenvalues, okay. Each eigenvalue goes with an eigenvector. Each eigenvalue goes with an eigenvector. But we can multiply the eigenvector by any scalar. And it is still an eigenvector. So let's try that. Okay, it's still an eigenvector with the same eigenvalue. Okay, so just to check, right, up here, right, we're trying out the eigenvalue 0, 1, but what if instead of 0, 1, we tried 0, 2? Okay, so twice that. Okay, so we could say, what is the matrix 1, 0, 0, 2 times the vector 0, 2? Okay, well, that matrix product is 1 times 0 plus 0 times 2 on top, that's 0. Okay, and then 0 times 0 plus 2 times 2, that's 4 on the bottom. Okay, so that is 2 times the 0, 2. Okay, so here the eigenvalue is 2, and the eigenvector is 0, 2. Okay, so it's not that the eigenvalue of 2 goes with a single eigenvector, but it's that the eigenvalue goes with a family of vectors that are all parallel to each other, right? That the eigenvalue 2 goes with 0, 1 or 0, 2, right? We could say, what if we multiplied by -1? What if we multiplied by -1? Okay, where's my eraser here? Oops. Okay, if we multiply by -1, we'd have 0 minus 1, like that. Okay, so multiplying this out, it's 1 times 0 plus 0 times -1. That's 0 on the top and -2 on the bottom. So that is still 2 times the vector that we started with, which is 0 minus 1. So instead of saying the eigenvalue goes with an eigenvector, I could maybe say instead it goes with a family of eigenvectors that are parallel to each other. Okay. So, if the question is, what's the eigenvector that goes with eigenvalue 2, right? You could answer 0, 1, or you could answer 0 minus 1, or you could answer 0, 2, right? There's an infinite family of correct answers to a question like that, right? Now, because there are lots of answers, there's a convention that we normalize eigenvectors. Just as we've been normalizing everything in quantum mechanics. And so we would say, let's choose the magnitude such that V conjugate dot V equals 1. Okay, so that means let's choose an eigenvector like 0, 1, or we could choose 0 minus 1, but not 0, 2, because it's not normalized. Okay. That's just a convention. This is still a correct answer to the question of what's an eigenvector that goes with the eigenvalue of 2, but it is not consistent with this convention. So conventionally, we would pick one of these guys because it's normalized. Okay, what else can we notice? Okay, there's more things to notice here. Okay, let's notice also that the eigenvectors corresponding to different eigenvalues are orthogonal to each other. Okay, so let's check that. We remember that the eigenvalue of 1 corresponds to the eigenvector 1, 0. Okay. And the eigenvalue of 2 goes with the eigenvector of 0, 1. Right. So now we could check, we can see that these two eigenvectors are orthogonal to each other. So if we say this is u and this is v, then u conjugate dot v is equal to 0. Okay. So there is that kind of orthogonality, right? This is a way of defining the inner product, the dot product, right? That we say 1, 0 conjugate with 0, 1. So that is the first times it's this thing times this plus this thing times that. So that is 0. Okay. One more thing that I can point out to you. Notice also that the eigenvectors are complete. That is, they form a basis for the 2D plane. That means that any vector in the 2D plane can be written as a sum, as a linear combination of eigenvectors. So that's one coefficient times 1, 0 plus another coefficient times 0, 1. So let's check that. Okay, so here I'll make up a vector. How about 2, 3? Okay, this is any old vector in the two-dimensional plane. All right, and this is equal to 2 times 1, 0 plus 3 times 0, 1. Okay, so that is expressing my arbitrary vector in terms of some coefficient, a coefficient times the first eigenvector plus a coefficient times the second eigenvector. Okay, so that works for this example, okay? And so you'll notice that I have like 5 general principles that I wanted you to notice, okay? I'll number them. 1, 2, 3, 4, 5. Okay, so 5 general principles. Okay, now these things are always going to be true. Okay, so let's try another example and we can see that those 5 things are still true. Okay, so let's try an example of a matrix like B is 0, 1, 1, 0. Right? So this matrix is not diagonal, right? It is a real symmetric matrix, okay? It's symmetric, meaning that whatever is northeast of the diagonal matches whatever is southwest of the diagonal. Okay, so we have that symmetry about the diagonal. Okay, so this matrix also has two eigenvalues. Now, if this were a math class, I would teach you things like how to calculate what are the eigenvalues. I'm not going to do that. I'm just going to tell you the answer and check it. Okay, and so my claim is that the eigenvalues are +1 and -1. Okay, and there's software that calculates eigenvalues, right? Mathematica calculates eigenvalues. Whatever software you like to use for doing math probably has an eigenvalue command. And so it could calculate the eigenvalues of this matrix. So let's check this, okay? So my claim is that we can find a vector corresponding to eigenvalue equal to +1. So let's try multiplying this times the vector 1, 1. Okay. So that gives us on the top 0 times 1 plus 1 times 1. That's 1. Oops. And on the bottom, 1 times 1 plus 0 times 1. That's 1. Okay, so this is equal to 1 times the vector that we started with. Okay, so here is the eigenvalue, and here is the eigenvector. Okay, and similarly, if we have 0, 1, 1, 0 times 1, -1, what do we get? All right, well, this matrix product is 0 times 1 plus 1 times -1. So that's -1. Okay, and on the bottom, it is 1 times 1 plus 0 times -1. So that is 1. Oh, and that is -1 times the vector that we started with. Okay, so in this case, -1 is the eigenvalue, and 1 -1 is the eigenvector. Okay, so now let's check the things that that I told you to notice. Okay, so we could check that there are 2 eigenvalues, which is equal to the dimension of the vector space. Well, yeah, that's still true. Right? It's a 2 by 2 matrix, and it has 2 eigenvalues. Great. Okay. We can check the eigenvalues are real. Yes, there's 1 and -1. Those are nice real numbers. All right. Let's see, what else were we supposed to check? We're supposed to check that you can multiply an eigenvector by any scalar, and you get an eigenvector still with the same eigenvalue. Okay, so that would be actually a good thing to do in this example, because the eigenvector is not currently normalized. Okay, so let's say the eigenvectors are not yet normalized. So if one of our eigenvectors is u is 1, 1, right? If we have u star dot u, okay, so that's 1, 1 star contracted with 1, 1. So that is 2. Well, that's not 1. Okay? But if we want to normalize the vector, we can divide by the square root of 2. Okay? So let's pick u prime is 1 over root 2, 1 over root 2. Okay? And then if I look at my matrix 0, 1, 1, 0, the matrix multiplication of that with 1 over root 2, 1 over root 2, that's equal to 1 over root 2, 1 over root 2. Okay, so it's 1 times that vector. Okay, so it is still an eigenvector with eigenvalue equals 1. And similarly, with the other eigenvector 1, negative 1, if we normalize it, we get v prime is 1 over root 2, negative 1 over root 2. Okay, what else are we supposed to check here? Right, well, we're supposed to check that the eigenvectors corresponding to different eigenvalues are orthogonal. Okay, so if we have u prime, my eigenvectors are this u prime is 1 over root 2, 1 over root 2, and v prime is 1 over root 2, negative 1 over root 2. Right? So if I take the dot product, so the first star dot the second, 1 over root 2, 1 over root 2, 1 over root 2, negative 1 over root 2. That's equal to a half minus a half, right? So it's 0. These things are orthogonal to each other. And I guess the fifth thing that I wanted to show is that the set of eigenvectors is complete. That is, it is a basis. Okay, so any vector in the 2D plane can be expressed as one coefficient times the first vector plus another coefficient times the second eigenvector. Okay, so let's try it out. Okay, so if I have my arbitrary vector like 2, 3, and I want to write that out as something times 1 over root 2, 1 over root 2, plus something times 1 over root 2, negative 1 over root 2, okay, with something in this blank and something in this blank. Okay. I can do that, okay? And so the way to figure out what goes in these coefficients is basically using the Fourier trick. That is, I take the dot product of both sides, the inner product of both sides with 1 over root 2, 1 over root 2. Okay, so if I do that, okay, on the, so this is C1, this is C2, okay? So on the left side of that equation, right, this 2, 3 inner product with 1 over root 2, 1 over root 2, that makes 2 over root 2 plus 3 over root 2. So that's 5 over root 2. That is equal to C1 times the inner product of 1 over root 2, 1 over root 2 with 1 over root 2, 1 over root 2, that's 1. Whoops, times 1 plus C2 times the inner product of 1 over root 2, negative 1 over root 2 with 1 over root 2 plus 1 over root 2. Oh, but that's 0. Okay, so it's C1 times 0. So that's C1. Oh, so C1 is equal to 5 over root 2. And then if I do the same thing with the other basis vector, 1 over root 2, negative 1 over root 2, let's see. On the left side, I have 2 over root 2 minus 3 over root 2. So that's negative 1 over root 2. And that's equal to C1 times 0 plus C2 times 1, right? So C2 is negative 1 over root 2, right? So to fill in these numbers, right here, this is 5 over root 2, and this is negative 1 over root 2. Okay, so that means, here we have two different ways of expressing any vector in the two-dimensional plane, right? And so, each matrix that we're working with, the matrix A or the matrix B, matrix A or the matrix B, gives us a way to express any old vector in the 2D plane. Okay? So let me try to draw that geometrically. Okay, so if I want to draw geometrically the eigenvectors of A, okay, that's a vector like this and a vector like that. Okay, so a vector in the x direction and a vector in the y direction. Okay, and by comparison, the eigenvectors of B 0, 1, 1, 0, that is a vector in this diagonal direction and a vector in this diagonal direction. And then if I have any old arbitrary vector like 2, 3, okay, I'll draw that one in red. Here's my arbitrary vector. Like 2, 3. Okay, so I can express the arbitrary vector in terms of the black vectors, or I can express it in terms of the blue vectors, right? If I want to express it in terms of the black vectors, I would say, well, it's like 2 of these black vectors and then 3 of these black vectors, right? That makes sort of the same thing. Okay, not the greatest drawing in the world, but something. Okay, so I can express the red vector in terms of the black vectors, or I can express the red vector in terms of the blue vectors. I could say it's some number of blue vectors like that and some number like that, okay? And, you know, what are they? Well, it's the things that I calculated on the last slide. Those are the coefficients. All right, so any 2 by 2 Hermitian matrix has this property, right? That any 2 by 2 matrix will give you a pair of eigenvalues and a pair of eigenvectors. And then you can use the eigenvectors to express any old arbitrary vector. Is this all familiar to you guys? Is this new for you guys? I can't quite tell here. Is this stuff like what you might have seen in a math class? Yes, okay. Is this totally obvious, or should I go on? Maybe I'll go on and do one complex example. Okay, so let's do one more example. Okay. Oh, yeah. Okay. Let's do one more example. Okay. So let's do an example of a matrix with some complex components. Okay, so how about if I have the matrix C, which is 0, I, negative I, 0. So this one is not real, right? And it's not symmetric either. But what we can notice is this matrix is Hermitian, as we defined it, to mean that it is equal to its complex conjugate transpose. Okay, so that if I do two kinds of flips, if I exchange the northeast and this southwest parts, and I also take the complex conjugate, I get back to the same matrix. Okay, is that property clear? Okay, so this matrix also has eigenvalues and eigenvectors. The eigenvalues, which I can calculate in Mathematica or whatever software, are +1 and -1. Okay, let's check that. Okay, so if I have the matrix C times a vector 1i, that is equal to, on the top, 0 times 1 plus I times I, which is -1. Okay, so it's -1 on the top. And on the bottom, I have -I times 1 plus 0 times I. So that is -I. This is -1 times the vector that I started with. Okay, so -1 is the eigenvalue, and 1i is the eigenvector. Okay, and what if I had this matrix 0i, -I0 times the vector 1, -I? That is equal to, let's see, on the top, 0 times 1 plus I times -I. That's 1. On the bottom, it's 1 times -I plus 0 times -I. So that's, no, it's not 0, that's -I. Okay, so this is equal to 1 times the vector that we started with. Okay, so 1 is the eigenvalue, and 1 -I is the eigenvector. Okay, so again, we can check the 5 things that I wanted to prove, right? And so we can check that there are, in fact, 2 eigenvalues. That's equal to the dimension of space, the vector space. And we can check that the eigenvalues are real. The eigenvectors are not real, but the eigenvalues are real. And that's a real theorem, that a Hermitian matrix has real eigenvalues. And then what else to check? We can check that we can multiply the eigenvectors by a scalar. And again, that would be a good thing to do because they're not currently normalized. Okay, so we can normalize them. Okay, so if we want to check the normalization, okay, if we have the vector u is 1i, right? And then the normalization is u conjugate dot u. And now it's actually important that we have this star there, the complex conjugate, because we have i's here, okay? And so this is 1i, this row vector complex conjugate times 1i. So that's 1 negative I times 1i. Okay, so this is equal to 1 times 1 plus negative I times I. Negative I times I is 1. Okay, so it's 1 plus 1. So that's 2. Okay. So the normalized eigenvector is, so u prime is 1 over root 2 times 1i, or I could say it is 1 over root 2 I over root 2. And this is still an eigenvector with the same eigenvalue. Okay, let's make sure of that. So we have 0, I, negative I, 0, matrix multiplication with 1 over root 2, I over root 2. So this is equal to, on the top, 0 times 1 over root 2 plus I times I over root 2. So that's negative 1 over root 2. Right? And on the bottom, we have negative I over root 2 plus 0. Okay, so it's just that. So this is negative 1 times the vector that we started with. Okay, so yes, it's good, right? That it still is an eigenvector with eigenvalue equal to negative 1. Right? And the other normalized eigenvector by the same argument is v prime is 1 over root 2 times v. So 1 over root 2, 1 negative I. Or 1 over root 2 negative I over root 2. Okay, that was the third thing I wanted to show in general. Okay, how about the fourth thing? The fourth thing is orthogonality. Okay, and so if we want to check that the eigenvectors corresponding to different eigenvalues are orthogonal. Okay. So we have the one eigenvector is 1 over root 2 I over root 2. The other one is 1 over root 2 negative I over root 2. So if we want their dot product, better again make sure we put the complex conjugate on the first thing. Okay. So u prime dot v prime. Okay, so that is 1 over root 2 I over root 2 star complex conjugate times 1 over root 2 negative I over root 2. So this is 1 over root 2 negative I over root 2 matrix product with 1 over root 2 negative I over root 2. So this is 1/2 and 1/2. And then the second product is negative I over root 2 times negative I over root 2. So that's minus 1/2. So it's 0. Okay, so it works out as long as we remember our complex conjugate times the first on the first thing. Okay, and then the last point is that the set of eigenvectors is complete. That is, any arbitrary vector is a linear combination. So it's coefficient times the first thing, so 1 over root 2 I over root 2, plus another coefficient times the second vector, 1 over root 2 negative I over root 2. So, for example, if my arbitrary vector again is 2, 3, right? I claim that there exists some C1 and C2 that make this equation true, okay? And if we want to find what those coefficients are, we could take the inner product of both sides with either of the eigenvectors. So, for example, 1 over root 2 I over root 2. Okay, so on the left side of that equation, this makes 2 plus 3I over root 2. Okay. On the right side of this equation, that's C1 plus this vector dot itself. We already know that's 1, plus C2 times this vector dot this vector. We already know that's 0, right? We worked out that orthogonality. So C2 times 0. So we know C1. It's 2 plus 3I over root 2. And similarly, if we do the inner product of both sides with 1 over root 2 negative I over root 2, Right? The same kind of argument gives us that 2 minus 3i is C1 times 0 plus C2 times 1. So it's C2. Okay, so C2 is this 2 minus 3i over root 2. And C1 is 2 plus 3i over root 2. Right? So the coefficients can be complex numbers, right? And they have to be in this case. But indeed, if you multiply this out, as I did in my notes just before class, because I was scared of getting this wrong, if you multiply all this out, right, you got all these things times that plus this times that. Yeah, it comes out to be 2, 3. Okay, so it's harder to draw that geometrically because it's hard to draw a vector which is a complex number in the x direction and a complex number in the y direction. I can't really draw arrows for that. But we can try to derive these things using our using real numbers, right, to get some concrete examples and try to develop an intuition, and then we can just use the math when it comes to complex numbers, right? And so the figure to remember is a figure like this one, right, where you can say each matrix gives you a basis, right? So one matrix gives you this black basis, another matrix gives you this blue basis, and then the C matrix gives you some weird imaginary basis. Okay? But you can use any basis to describe an arbitrary vector. Okay, with coefficients that you can work out. Okay, so these are a few examples to think about in terms of 2 by 2 matrices. Okay, now we can do the same thing with 3 by 3 matrices. I'm not going to, but we could, right? And it would work with 3 by 3 matrices as long as we make sure to do 3 by 3 matrices that are Hermitian. That is, they're equal to the complex conjugate of the transpose. Okay? So one subset of that is we could do 3 by 3 matrices that are diagonal. Okay, so here's 1, -3, 4, right? 0, 0, 0, 0, 0, 0, 0. Okay, so this is one where you can just read off the eigenvalues, right? That the eigenvalues are equal to 1 and -3 and 4. Right? Here, I'll write that down. So the eigenvalue of 1 goes with the eigenvector of 1, 0, 0. The eigenvalue of -3 goes with the eigenvector of 0, 1, 0. The eigenvalue of 4 goes with the eigenvector of 0, 0, 1. Yeah, so diagonal matrices are great because you don't have to do any computation. You can just read off the eigenvalues. that's why, I like to do things like this on test problems. That a good test problem is, what are the eigenvalues of some diagonal matrix? Because that checks if the student, recognizes what's going on. Okay. Or, we could do a 3 by 3 symmetric matrix, a real symmetric matrix. So something like, I don't know, 0, 1, 2, 3, 5, 0, 1, 2, 3. Here's a symmetric real 3 by 3 matrix. Okay, so it has 3 eigenvalues and corresponding eigenvectors. And I absolutely cannot work them out of my head, but we could type this into Mathematica or something, and Mathematica can work out what they are, right? Or we could do a 3 by 3 complex Hermitian matrix, like 0, 5, 0. It better be real on the diagonal. Okay, and then I could say I, 2i, 3i, negative 2i, negative 3i. Okay, that's a Hermitian matrix. Right. Again, I cannot calculate those eigenvalues and eigenvectors in my head, but software can. Now, these matrices have all the same 5 properties that I was trying to show you before, right? That the eigenvalues are going to be real numbers. The eigenvalues, there are going to be 3 of them, right? And because it's a 3 by 3. The eigenvalues, you can multiply them by a scalar and they still work. Right? So in particular, you can normalize them and they still work. The eigenvalues correspond, the eigenvectors corresponding to different eigenvalues will still be orthogonal to each other. Right? And then the set of eigenvalues, the set of eigenvectors can form a basis for 3-dimensional space. Right? So you know that these 3 vectors are a basis for 3-dimensional space, right? People sometimes write them as x hat, y hat, and z hat, or sometimes you call them I hat, j hat, and k hat. All right, so it's 3 mutually perpendicular vectors in the x and y and z directions. Right? If I calculate the eigenvectors of this real symmetric matrix, I don't know what they are, but whatever they are, I can guarantee you I can represent them with my fingers like this, okay? Just with my hand tilted in some direction, okay? There are going to be 3 mutually perpendicular vectors, right? And then any arbitrary vector in 3 dimensions, like my Apple Pencil, can be written as a linear combination of something times my thumb plus something times my index finger plus something times my middle finger here. Okay? So that is the 3 things make a basis, a way of expressing an arbitrary vector in 3-dimensional space. Okay? And likewise for the complex Hermitian matrix, well, it kind of works as long as I have, complex fingers, right? That point, that go off in complex directions, but the same general idea works. It's the same mathematical concept, but with complex numbers instead of real numbers. Okay. So it works with 3 by 3s. It works with 4x4s. It works with n by n's, right? With matrices of any dimension. There is one little footnote, I'll say, the fine print, okay? So the fine print, the little legal disclaimer that they have to say in any kind of advertisement, right, is that eigenvalues might be degenerate. That is to say, the same number appears twice or more than once. Okay, an example of that in a 3x3 matrix would be a matrix of 1, 1, 2. Okay, and so in that case, we would say the eigenvalues are 1 and 1 and 2. So, 1 counts twice. So I just don't want any student, coming back and arguing with me and say, wait a minute, you told me there were going to be 3 eigenvalues, but there are only 2 eigenvalues, 1 and 2, right? And that's when I sort of say, well, 1 counts twice, right? And so it's like saying with a quadratic equation, right? We know a quadratic equation has 2 solutions, but in certain special cases, the 2 solutions can actually be the same number, right? And so it sort of counts as 2 solutions, right? But we have to double count one of them. So the same thing here, right? 1 counts as 2 solutions there, as 2 eigenvalues. So that's the fine print in counting the eigenvalues. That has to go along with my disclaimer. Okay, so that's 5 principles that I wanted to illustrate to you with working with matrices. Okay, so for the eigenvalues, that they're real, that the number of them is equal to the dimension. And for the eigenvectors, you can rescale them, you can see the orthogonality, and you can use them to make a basis for all space, okay? So, it's 5 principles, but, it's only half as many as Moses had. What I'm going to do next is to show you how the same 5 things work for operators, okay, in quantum mechanics. So I'm going to talk about how to do Hermitian operators and see that the same 5 things also work. So I'm out of time for now, so I've got to do that tomorrow. Okay, so let's stop here, and I'll see you guys tomorrow for doing that kind of stuff, okay? Great, so long.